Hello everyone, myself Sanika Parathe. Today I will cover chapter 9 from Ismail Tosun, and the topics covered are laminar force convection in a pipe and diffusion into a following liquid film. First, we will see problem based on laminar force convection in a pipe. This problem is from mass transfer with a convection in a pipe. Here, a fluid is flowing through a circular pipe and species A is transferring from the pipe wall into a flowing fluid. Here, mass transfer occurs due to the concentration difference between wall and bulk fluid. So, we will apply a mass balance on a differential element and prove that both laminar and turbulent approaches give the same governing equation. Given pipe of diameter d, thickness delta z and cross-sectional area pi d square by 4. We will apply a mass balance equation, that is mass in minus mass out plus generation equal to accumulation. So we consider a steady state, therefore accumulation is 0 and there is no reaction taking place, so the generation is also 0. Therefore rate in equal to rate out. Now we will see mass in at distance z, that is Q, that is volumetric flow rate into concentration at z, and mass out, that at z plus delta z, that is Q, that is volumetric flow rate into concentration at z plus delta z. And we will see mass entering from the wall. This is the mass transfer from the surface into a bulk. So the rate equation will become Kc into surface area into driving force. Surface area can be calculated as pi into diameter into thickness, that is delta z, and driving force is concentration at the wall minus concentration at the bulk. After combining it into a balance equation, we will get the equation that is rate at z plus rate from the wall equal to rate at z plus delta z. After rearranging the equation and dividing the equation by delta z, and integrating it, we will get the final equation, that is Q delta CAB by delta Z equal to pi d into Kc into driving force. Which is identical to equation 1. Now we will see part B, which is packed bed of particles. In this, the pipe is filled with particles and the mass transfer occurs from the surface of all the particles within the volume element. We will again apply a mass balance equation, that is mass in at z minus mass out at z plus delta z plus mass transfer from packing equal to 0, and volume of element is V equal to A into delta z, where A is pipe cross section and the total surface area of the particle in this element is AV into area into delta z. Again the rate equation will be Kc into surface area into driving force. Again by applying a mass balance equation and rearranging the equation, and dividing it by delta Z, we will get the equation that is Q into delta Ca by delta Z equal to AV Kc into driving force, which is reduced to equation 1 for a circular pipe having area pi d square by 4 and AV equal to 4 by d. If we substitute these two equation into above equation, we will get the final equation, which will reduce to equation 1, or which is identical to equation 1, that is Q into dCAB by dZ equal to pi d Kc into driving force. Moving to question 9.16, this problem involves a diffusion of oxygen through the wall of a cylindrical tube into a flowing liquid. Again, we will consider a differential element and apply a steady-state mass balance equation. In this question, the given data are: inner radius is R1, outer radius is R2, bulk concentration is CAB, surrounding concentration is Ca infinity, and flow rate is Q. In part A, we will derive governing equation. We will apply a mass balance equation, that is rate in minus rate out plus diffusion equal to 0. So the flow at Z minus flow at Z plus delta Z plus diffusion through a wall is equal to 0. Bulk flow in is flow rate into concentration at B, and bulk flow out is flow rate into concentration at Z plus delta Z, and diffusion through a wall is the rate of diffusion through a cylindrical shell, that is plastic tube of length delta Z, is given by WA equal to 2 pi into delta Z, that is thickness, into diffusibility DAB upon ln R2 upon R1, that is outer radius upon inner radius, into driving force. Combining into a mass balance equation and rearranging the equation, will become 2 pi into delta Z by D into DAB upon ln R2 by R1 into concentration at surrounding minus bulk concentration equal to flow rate into concentration at Z plus delta Z minus flow rate into concentration at Z, and dividing the inter equation by delta Z, we will get this equation as delta Z is infinitesimally thin, so delta Z tends to 0. And the equation will become Q into dCA by dZ equal to 2 pi into diffusibility upon ln R2 by R1, that is outer radius upon inner radius, into concentration, surrounding concentration minus bulk concentration. In part B, we will integrate to find the concentration profile by separating the variable and by taking the limit at Z equal to 0, that is bulk concentration will become Ca0, and at Z equal to Z, bulk concentration will remain same. By integrating, and with appropriate boundary condition we will arrive an exponential expression for concentration. These results show that the concentration of oxygen in a liquid approaches the external concentration exponentially as the tube length increases. This expression shows that the tube length increases, the concentration in the liquid exponentially approaches the outside air concentration, that is Ca infinity. As the fluid flows forward, concentration gradually increases and finally approaches outside concentration, that is Ca infinity. Moving to our next topic, that is diffusion, into a following liquid film, we will see a problem based on this topic. In this problem, we analyze that the absorption of hydrogen sulfide gas into a water following liquid film. The first step is to calculate the film thickness using a Nusselt theory which relates fluid property and flow rate. Once the film thickness is obtained, we will calculate the average velocity of the liquid film, and then from this average velocity we will determine the contact time, which represent how long the liquid is exposed to the gas. The given data is flow rate, that is 6.5 into 10 raised to power minus 6 meter cube per second, length is 2 meter per second, width is 0.8 meter, and diffusibility is 1.3 into 10 raised to power minus 9 meter square per second, and solubility is given as 0.1 kilomole per meter cube. Properties of water at 20 degrees Celsius, that is viscosity 1.3 into 1 into 10 raised to power minus 3 Pascal second, density 1000 kg per meter cube, and gravity is 9.81 meter per second square. From film thickness, that is from Nusselt theory, delta equal to 3 into viscosity into volumetric flow rate upon density into gravity into width whole power 1 by 3. From this we will get film thickness. After calculating the film thickness, we will calculate the average velocity of the film by the formula rho g del square upon 3 mu. After calculating the average velocity of the film, we will calculate the contact time by dividing viscosity, length by viscosity. After calculating the contact time, we will calculate mass transfer rate using Higgs penetration theory, that is Na equal to 1.128 into stability into under root of diffusibility by time. By calculating the mass transfer rate using Higgs penetration theory, which assumes unsteady diffusion into a moving liquid element, the molar flux is proportional to the square root of diffusibility divided with the contact time. After substituting all the value, we obtain the flux of hydrogen sulfide, and multiplying this flux by the rate of the plate gives the total absorption rate. As we have seen, first we will calculate the area of the plate by multiplying length into breadth. After calculating the area, we will multiply it by NA to obtain absorption rate. A correction factor is then applied to account for practical deviation, yielding the final absorption rate. So in this case we have taken correction factor as 0.58 and then multiplying with the rate, absorption rate, we will get a corrected rate. If the contact time increases, absorption will be more, and if the diffusibility increases, faster absorption will take place. Moving to our next problem, based on diffusion into a following liquid film, we will consider the absorption of carbon dioxide in a weighted wall column. The approach is similar to a previous problem. First, we will calculate the weighted perimeter of the column and then determine the film thickness using Nusselt equation. Next, we will compute the maximum velocity of the liquid film, which is required for the mass transfer calculation. The given data is diameter D equal to 5 cm is given, so we will convert it into meter, that is 0.05 meter. Height L equal to 1.5 meter. Flow rate Q equal to 8.5 into 10 raised to power minus 6 meter cube per second. Solubility, that is Ca star, equal to 0.0336 kilomole per meter cube, and Ca naught equal to 0 because pure water. Properties of at 25 degrees Celsius, that is viscosity equal to 0.89 into 10 raised to power minus 3 Pascal second. Density of water equal to 1000 kg per meter cube. Diffusibility 2 into 10 raised to power minus 9 meter square per second. First, we will calculate weighted perimeter, that is W equal to pi into diameter equal to pi into 0.05 equal to 0.157 meter. Then we will calculate film thickness by Nusselt equation, that is del equal to 3 mu q by rho g w whole power 1 by 3. Substituting the value, we will get a film thickness of 2.47 into 10 raised to power minus 4 meter. After calculating the film thickness, we will calculate maximum velocity by using the formula rho g del square by 2 into viscosity. Substituting the respective value, we will get a maximum velocity of 0.336 meter per second. Now applying rate equation, that is Na equal to weighted perimeter into length into concentration difference in under root 4 into diffusibility into maximum velocity upon pi into length. Substituting the value, we will get a rate of 1.87 into 10 to the power minus 7 kilomole per second. The rate of absorption is then determined using an equation that incorporates weighted perimeter, column height, concentration driving force, diffusibility and velocity. Substituting the given values, we will obtain the final absorption rate of carbon dioxide. In conclusion, this problem demonstrates how mass transfer principles such as convection, diffusion, interfacial transport are applied in real engineering systems like pipes, film, and absorption column. They also highlight the importance of steady-state analysis and use the appropriate theoretical model such as Fick's law, Nusselt theory, etc. Now we will see a derivation on diffusion of a gas into a following liquid film flowing over a vertical surface. The system consists of incompressible Newtonian liquid B flowing downward as a thin film of thickness delta under the influence of gravity, while the gas flows in opposite direction and diffuses into the liquid. To describe the system, we define a coordinate system where the x direction is perpendicular to the film, representing the direction of diffusion, and the z direction is along the flow of liquid, representing convection. The analysis is based on steady state condition, laminar flow, and there is no chemical reaction, and the assumption that diffusion occurs in x direction while convection occurs in z direction. The velocity profile of the liquid film is parabolic and is given by Vz equal to Vmax into 1 minus x square by del square. This expression shows that velocity is maximum at the free surface and 0 at the wall. Next, we will apply Fick's law of diffusion. In the x direction, the molar flux is given by minus dAB dCA by dx. In z direction, molar flux includes both diffusion and convection term and is expressed as minus dAB dCA by dz plus concentration into velocity. At steady state, the net accumulation is 0. So, the continuity equation becomes the sum of the gradient of molar flux in x direction and z direction equal to 0. Substituting the expression for flux into this equation and simplifying, we obtain a partial differential equation involving second derivative of concentration with respect to both x and z. That is Vz dou Ca by dou z equal to dAB, that is diffusibility, into dou square Ca by dou x square plus dAB, that is diffusibility, into dou square Ca upon dou z square, that is convection in x direction equal to diffusion in convection in z direction equal to diffusion in x direction plus diffusion in z direction. Rearranging the equation, we see that convective transport in term in z direction is balanced by diffusion term in both x and z direction. However, for high Pillet number condition, convection dominates in z direction and diffusion in z direction becomes negligible compared to convection. With this simplification, the governing equation reduced to a form where the convective term involving the velocity profile and concentration gradient along z is equal to diffusion term in x direction. Substituting the velocity profile into this equation gives the final expression which relates the change in concentration along the flow direction to diffusion across the film thickness. This equation represents the fundamental balance between convection and diffusion in the following liquid film and form the basis for analyzing gas absorption in such system.